Exercise 121. Let's talk about exterior groups. So, first, quickly recall that you could compute this in several different ways. So, more precisely, let's keep two abelian groups, A and B. So this is defined to be this exterior is defined to be the derived functor of home functor, right? So you could either using this as covariant functor from the module to abelian groups, or take this functor from as contravariant functor from the module to abelian, or as a covariant functor from the op of the module to abelian. And they are left exact functors. Let's see, left exact covariant functors. And so they have right derived functors, the exterior. Think of it in this way. Let me summarize. Extra functors for each R module A. The functor f of b defined to be, so this is a more general situation. In other words, this f corresponds to this factor, right? Is left exact. So right derived functors are called extra groups. Let me put sub-remark. In particular, extra 0 AP is home AP so before we do the exercise, let me put a sub-exercise. talked about this. So last time we talked about projectives. Similarly, you could have discrete injectives. Probably we will discuss also the injectives, but so let's first see this sub-exercise showing that the following are equivalent. So again, we are following Weibel's book on homological algebra. Firstly, this R module B is an injective R module. Secondly, this functor is an exact functor. So in general, this is just a contravariant functor from R modules to abelian groups, or covariant functor from the opposite of R modules to abelian groups. Third generalization, can use exterior groups. So this vanishes for all I non-zero and all R module A. So we will see that symmetrically when A is projective, this is also vanishing for any B. So this is, in other words, this is saying that this is cyclic. You could see that A is a cyclic for any A. Well, here is already obvious. When you have exact functor, then obviously write that projective resolution after you apply this functor is again exact and so cyclic and so trivial homological groups. Secondly, very symmetrically, similarly, so the following are equivalent. A is projective. Module. Secondly, this is the exact functor. Thirdly, sorry, let me add one more. So here, extra one vanishes. So obviously C implies D, but actually this is equivalent. Usually, I mean, I don't think this changed something, but let's change it to left arm module, which is we're more familiar with that. That's our convention, right? Talk about our modules usually without mention. We already always apply the automorphism, endomorphism comes from the ring R on the left hand side. So correspondingly here, vanishes for I non-zero, because I equals 0, this is just home AB. Equivalent, you could say that A is B is home sorry, A is a cyclic for any A. Sorry, obviously here we're talking about this B because A is fixed. My understanding, this is B is a cyclic for any B. Correspondingly, this vanishes for any B. So here, let me just quickly recall that. Our object is said F a cyclic, F is a functor. So let's see. Q is called F a cyclic if if q equals 0. The left derived functor of f. So f, of course, we assume it to be right exact here. I mean, here it is not the case we're talking about. So actually here we should talk about left exact functors, right? This is just take an example. And so because this B is special, it's injective. So looking at this functor, of course, you could also say that B is home A, like this, right? And then you fix B, cyclic. But anyway, I mean, here you must fix B, because B is special injective. Here you must fix A. I mean, you could also say that B is, for this B is always home A bar acyclic. This also makes sense. It's just terminology for whatever A, right? It's just terminology. Okay. So I'm not going to give proof of this. So it's very easy to remember the result, but the point is you have to remember the position, projective on the first position and injective on the second position. Let's say to help remember the situation, let's connect the fact that for example, let's show that home A R is an exact functor if and only if, so A is projective. So let me just prove one direction. So let's say, let me prove this direction. Just to quickly, when we forgot the position of projective and injective, so this use the definition project to quickly remind ourselves. So projective means, recall that if you have for any surjective map in our modules, let's say xy, and then for any gamma, let's call this j, there exists map data to make this community, right? This is a definition for universal property of projective. And let's say why this implies this is exact functor. So let's take a short exact sequence in our module, and we know that this covariant version is always left exact. So the problem is, can you show that this is surjective, right? This is the question. And then this just comes from the universal property. So what you have is, you have a surjective map from Y to Z, and then I'm asking you that given a map from A to Z, is it in the image? So this map is mapping F to, by the definition of the whole map, a Y, YZ, this is composition. Let's call this YZ G. This is just a y and then y is decomposed with f, which means this map surjective. So the question is, given any map from A to Z, is it equals to some G compose F? Yes, it is, because there is some beta, then take let G to be this beta, and then the universal property is exactly telling that this is the image. As actually you see, this is actually telling you that we have this. Because it is projective if and only if we have the universal property, and the universal property is telling you that this universal property if and only we have this universal property if and only if this is surjective. And this help you, not that short and quickly, but this help you to locate the position of A should on the first position. I don't know, there should be some better way, but it's always very easy to forget. Okay, then let's do the second exercise. Let's do some computation. You can think of this as a small lemma. We'll claim that external groups abelian groups for any abelian groups AB is always 0 for n bigger or equal than 2. And whatever AB abelian groups. Proof. So I'm going to use a fact. The fact is that we have chapterization of injective modules for principal ideal domain. Let me put it here. So let me put it as a sub exercise. So perhaps we'll prove this later. If R is Z, so we'll talk about our modules as abelian groups, or any principal ideal domain, then I will give a chapterization of the injectives. R is injective. It's injective in this category of our modules if and only if it is divisible. Let me put also a second one under the similar situation is flat if and only if it is torsion free. Okay, so let's just use the description of the injective here. So let me compute. So I start with, I'm going to look at this position. I'm going to take the injective resolution way. So basically, what we are going to do is that take this functor. This is left exact from the opposite category of normal due to happening groups. It's left exact, and so you take right derived functors. The left exact functor applies on injective resolution of A. Right, have injective resolution. I apply a left exact functor take this injective resolution in R mode. Then this corresponds to a projective resolution. It's opposite category. Sorry, I got the wrong direction. So if you want to use this, then you should take projective resolution of A. This is in opposite category of our mode, and then this corresponds to injective resolution in our mode, and then you have a left exact functor that you apply it. This again gives you exact for the first few terms. This is the reason that the derived functor 0 is the same as f of A, isomorphic to f of A. Or equivalently, you could take this functor, covariant functor. So this is left exact functor. Here doubling groups. And then you could take an injective resolution of B. And do the similar thing. But now I claim that, let me take the second version. I claim that this is an injective resolution B because I0 by the category happening groups. This is injective, which means this is divisible. And this implies that this is again divisible. And so this is again injective. So this is injective resolution. This is exact sequence, and this is injective resolution. And then you apply the functor, compute its derived functor. This will give you home B, and then by definition of the derived functor, what you do is you're just going to compute the cohomology of this, right? Cohomology of this gives, by definition, this group, and this gives you the proof. Exercise 3. Compute more precisely we mean this, of course. When you got your projective or injective resolution, then you move out the module and then you add 0 and then right. Then this is the complex you're going to compute its cohomology, but here this is exactly this. Totally 0, so it's only concentrated on the first position, and this I1 here corresponds to the I1 corresponds to I0 quotient B, and then you apply F, you got this. I use this bracket to mean the complex concentrated in degree 0 and 1. Okay, so compute exter 0 for the quotient P compute x1 sigma p for any happening group B. So we do the computation, compute our solution. Actually, so there are two different ways. Firstly, is you could apply to the previous examples. So apply A equals sigma P to exercise 2. And then what you get is that you only left to compute the cohomology for this. Let's look back a little. Very similar argument. Let's take a resolution. So, because we don't know what is B, but we know what is A now. We know what is A, then if you look at the position of A, we know we should take projective resolution. So we're going to consider projective resolution as a Z module, so subjective, and then we have this short exact sequence. So notice this is a projective resolution. Sigma P, and so you just apply a functor, right? And then you know how to compute extra groups. So it only left to compute how right, because project resolution is, so we're going to apply a functor on this. This is a contravariant functor, so it gives back to, and then compute the cohomology of this. I mean, you just compute the cohomology for this, and then so this is telling you that it's degree 0, degree 1, and then this is telling you that, okay, so you're applying the functor this. So for A, when you apply this functor, you got this. So that's the kernel of P. Right, notice that this is isomorphic to B, and the corresponding map is exactly multiplication by P. And so this is just those elements of B killed by P. Right, and then here corresponds to x star 1, x star 2, it corresponds to kernel quotient image, right, and then all the others are 0. So this is the first solution. What I was thinking for a while is that in my mind I'm having that short exact sequence. So you could also, another solution is that, okay, you don't care this is projective resolution or not, you just have this short exact sequence, and then you have short exact sequence, it induces a long exact sequence. For this induces long exact sequence. I mean, I should say this as a direct as delta functor. So here I should be more precise. This induces a long exact sequence. Right, so you have this. This is like x star 0. And then you have x star 1. X star 1. So, and then you have x star 2. And so on, but we know all the x star 2 becomes 0. And here what we know is that this is isomorphic to B again. And moreover, we want to compute this, but this is 0. The reason is our sub exercise before. Z is projective. When the first position is projective as a Z module, in general R module, or the second position is injective as R module, then the extra group store vanishes. This is what we mentioned here, right? And so without computation this would be 0, and so finally this is just telling you that exactly this is your x star 0, and then you have B, and then you have your x star 1, and then you have 0 here. Exactly, this is telling you that this isomorphic to the kernel of multiplication by p, and this is the co-kernel, which is b quotient by pb. Let's give you the same result. So let's do one more exercise. Exercise 4. Let's talk about the extension. So let me first recall. The extension, let's call it C of some R module A by R module B is a short exact sequence. So let's say C 0 to of A by B of A by B. So let's put B here. E corresponds to extension. So here it is an extension. E is called extension of A because it's come back to A modulo B, but it's kind of lift A, right? And two extensions, let's say CX prime are equivalent if we have a commutative diagram of this kind. So you have identity on A and B, and then isomorphism on the middle term. So let me call this A, B, definition A, definition B, C. C is saying that extension is trivial or split. If it is equivalent zero B plus B A 0, which means elements map to the second position. This is just a projection map. Okay. Now the exercise is show that if P is prime, then there are exactly P equivalence classes of extensions of Z mod P by Z mod P. Otherwise, I'm claiming that this is isomorphic to. Wait, I'm not requiring that. I'm only talking about their P equivalence classes. Yeah, as I said, I mean, it's projective is a set of P elements. Actually, we will see that this is also so this is later. So let me put this exactly equivalence classes of Z mod P by Z mod P. Actually, so this this is actually there is a 1-1 correspondence between this set and extra groups. Actually, this is true in general, only for Z1P, Z1P. This is more general. I'm not giving it a group structure now. I'm only saying that they're up to isomorphism. This is a equivalent class with equivalent relation, and they're P equivalent classes. So how am I going to do that? Firstly, so with this sub-exercise, can I know at least the cardinality of the equivalence classes, right? This is just, so in our case, this is at Z module. So this is, by what we have done in the last exercise, this is just isomorphic to, remember we put B here, then one is just B mod P with B here equals Z mod P, right? And so this is just Z mod P itself. And so at least you know that the cardinality is P. So there should be P equivalence classes. And then we just notice that, okay, so if you have an extension of Z mod P to some abelian groups and then Z mod P, then again by the group theory, then the cardinality of E would again be P squared, right? Because we have this. So this is not free, no, not direct experiment free, so this would not split in general. Let me think. Yeah, would not split in general. And there are two possibilities by the structure theorem of abelian groups. Maybe I'm doing this too complicated, maybe it's much easier. So it would be just either it's this or it's this, right? And let's first talk about the second. Notice that we have equivalence classes as follows. So here I'm going to multiplication by P, which I mean map X bar which I mean just the embedding. The embedding is, sometimes people write it multiplication by P, but I feel it's confusing to write it multiplication by P. What I really mean is that this thing as P times Z mod P squared, then it embeds naturally into Z mod P squared, okay? And then I construct an isomorphism to firstly start with the morphism of this. You only have to decide what is a major one, right? And to be surjective, actually you could map it to either 1, 2, 3 until P minus 1, because they're co-prime with P, and it's easy to see that either of this would be surjective. What does this mean? This means that I've constructed already P minus 1 extensions, so each one is of this form. Multiplication by I. So this is Z linear. Once you determine what is a major 1, you determine. This means 1 is mapped I. And somehow I have to also to show that I'm claiming they corresponds to p-1 different equivalence classes. If that is the case, because the cardinality of the extension extra group is only p, and there is only one left, it would be the splitting one. So what you left show is that those given by different I corresponds to extension that are not equivalent. Let's just take two examples, 1 and 2. There exists something that makes this commutative, so 1 is mapped to 1, and then by identity this is mapped to 1, and then 1 who is mapped 1. Nobody will map to 1, right? Because here 1 is mapped to 2. Wait. Yeah. Yes, who is mapped to 1? As I said, this will be surjective. Let me just take a precise example. Let's see what happened. Let's say p equals 3, and then symbol 9, then this symbol 3, symbol 3, 9. So if you map 1 to 2, then who is mapped to 1? So the point is that 2 and 3 are co-prime, so notice that 3 minus 2 equals 1. This is telling you that minus 1 is mapped to minus 2, which is the same as 1. And then minus 1 is mapped to 1, 1 is mapped to 1, 1 is mapped to 1, and will this be equivalent if I just will be an isomorphism, I map 1 to minus 1. Will this be isomorphism? What would then be the problem? The problem, I don't think here we have problem. Same, this is still, yeah, morphism, but look at here. So here you have, say something is 3z mod 9, 3z mod 9, and then identity. So here you are. For example, 3 is mapped to 3, and 3 is mapped to minus 3, but here 3 is mapped to 3, 3 should be mapped to 3 but not minus 3. This is not commutative. And so actually you don't have choice. So this is not isomorphism to make the diagram commutes. It is isomorphism, it will not make the diagram commutes. And so this shows that actually you have p minus 1 not equivalent extensions. And finally, notice there is one more by split. This is also extension. Altogether you already find p non-equivalent extension. So this is not isomorphic to either of them, not even as z module, so we don't have to compare them. And so finally you got all the p equivalence. You have all the p equivalence classes.